Welcome back. I'm that chemist, and today we're going to be ranking the oxidants, and I have some really special ones in there that you might not be familiar with. So without further ado, let's get started. So the oxidants that we're going to be ranking today have to be relatively common ones. Some of these have specific applications, but overall, if they're included and they're not that common, they're pretty meme compounds that you might want to be familiar with. Additionally, we're going to be considering how useful they are as an oxidant, so how much you want to work with them, how much cool stuff you can do with them, etc. So let's get started. Let's start with a nice easy one like DMSO. Now you might not think of DMSO as an oxidant, but because it's a sulfoxide that can be reduced to a sulfide, it's able to oxidize stuff. So you see DMSO used as an oxidant for Swern oxidation, corn bloom oxidation, as well as several other examples. Now, it's pretty stable most of the time, and so for that reason it's nice. However, when you use it as an oxidant, it generates dimethyl sulfide as a byproduct, which really stinks. And so for that reason, we're going to put it in D tier, D for DMSO. Now let's look at another one like PITA. So PITA is this Diacetoxy Iodo benzene. Now this is a decent oxidant. You can also do some cool reactions like de-aromatizing benzene rings with this. So this is kind of cool. It's got some niche applications. If you need to activate it, you can occasionally exchange out the ligands with other carboxylate ligands. It's pretty decent. It hasn't seen as much utility as it could. And so for that reason, I'm going to put it in E tier. So let's look at another one like nitric acid. Nitric acid has a strong place in everyone's heart. Nitric acid can dissolve copper really easily. It can also be combined with hydrochloric acid to make aqua regia, which is royal acid, right? So a royal water, super cool acid. I think nitric acid probably has to go in S tier because it's like one of the coolest oxidizers to work with. Now, what's kind of cool to work with as well, which also generates brown gas, is bromine. So bromine, Br2, it's a pretty decent oxidant. Sometimes certain things can get oxidized too quickly with it. So for instance, if you combine bromine with aluminum foil, you'll get aluminum tribromide in an extremely exothermic reaction. Bromine can also do several other types of oxidation reactions. However, a lot of the time when we see it in organic chemistry, it would be used as a brominating agent, not strictly as an oxidant. So because it does some other chemistry, we're going to have to give it a slightly worse grade, and so we'll put it in B tier, B for bromine. Okay, so another hypervalent iodine reagent is IBX. So IBX is nice as an oxidant because it's not that soluble in organics. So you can still do oxidation chemistry on the surface of the solid, but you won't have to struggle to get rid of the IBX after the reaction, even in its partially reduced form. So it's a decent reagent for that reason. Now, it's a little bit annoying to prepare, but it can be prepared easily enough. Occasionally, people have prepared this using sodium bromate, which is really toxic, and it generates bromine as a byproduct. However, there's newer methods that have been developed using Oxone, which unfortunately Oxone isn't on this list. And if you think Oxone should be included in here, make sure you let me know down below. So I actually really like IBX, and since it has a B in it, we'll put it in B tier. Okay, so there's some other cool ones. So you might not have seen perruthenate before, but perruthenate is a really good oxidant. It's pretty expensive because ruthenium is a precious metal. So when ruthenium-based oxidations are done, they usually use a different reagent to oxidize the ruthenium back up to perruthenate. And so that's usually N-methylmorpholine N-oxide. So tetrapropylammonium perruthenate, it's a really cool oxidant. It's kind of like DMP or Swern in terms of making aldehydes or ketones. I really like this one. I haven't personally used it, but I think it's a really useful oxidant. And so for that reason, I'm going to put it in S tier. N-methylmorpholine N-oxide is used to turn it over. Now, on its own, it's not that cool of an oxidant. However, because it's used in the perruthenate oxidation as the regenerating oxidant, I think it probably deserves at least a C tier grade. Now, I mean, that being said, DMSO only got D tier, so I think we're going to put DMSO into C tier, even though DMSO starts with a D. However, we have some cool ones here, like manganese heptoxide. So I have a couple videos on my old channel which feature manganese heptoxide burning some solvents like hexane or cyclohexane. Manganese heptoxide is a crazy strong oxidant. It can generate ozone when it decomposes. And how many chemical means of synthesizing ozone can you think of? Yeah, not that many. Manganese heptoxide, S tier. One of the best oxidants. Terrifying to work with though. Someone in the Discord, when we were talking about the idea of this video, was saying that they had an entire fume hood get destroyed in one of their grad courses as a consequence of a manganese heptoxide demonstration by an instructor. So it's no joke. It's quite a terrifying chemical. I've also tried putting a little bit of a plastic polypropylene Eppendorf in some manganese heptoxide, and it sizzled and it made a couple flashes making ozone, but then it just detonated a giant hole in the side of it. So manganese heptoxide is terrifyingly strong. Now another famous oxidizer is perchloric acid. It's a little bit too terrifying, especially when you work with it in its, higher concentrated form. People say that if you work with 70% or less, it's relatively safe, but above that, it's pretty terrifying. Now, I personally haven't worked with perchloric acid, but most of the time when you do work with it, you have to have special considerations because of how potent of an oxidizer it is. So perchloric acid's pretty terrifying. You don't really want to handle it, so we'll put it in C tier. Now DMP. DMP can go right into S tier, and if you want to know why, you can go watch my DMP oxidation video, which I'll put a card to here. Now, you might be confused why I included water in this list. Well, as you may know, water can actually oxidize certain transition metals and other compounds to oxidized states. You have an aqueous solution, slowly the water can oxidize stuff. Now, you might say the oxygen in there, like oxygen gas, is actually what's doing the oxidation. However, water can be an oxidant on its own if it's reduced by a metal. And so when it's reduced, it generates hydrogen gas, so it's still technically an oxidizing agent. So because water's in soda, we're going to put it in S tier. We're still trying to make up for the acid video where water was mistreated and water didn't get put into S tier. Now, there's some other really good oxidizing agents like the halogens. We also have talked about bromine already, but let's talk about chlorine. So chlorine gas is terrifying. I have worked with it and generated it several times. You might be familiar with chlorine for several of the different reactions it's known for. It's a little bit too hard to handle on its own, so while you can work with a cylinder of it, that's pretty terrifying, so it's usually better to generate small amounts of it as you need it. The other terrifying thing about chlorine is normal people can make it very easily, and so that's a little bit scary too. So for that reason, I'm going to put chlorine a little bit lower. It's a really good oxidant though, but because it's a little bit too hard to handle, I think it probably belongs in C tier. Now, iodine is kind of a sucky oxidant, but that could be good, right? There's applications where you just barely need something to be oxidized, catalytically maybe even, so iodine's pretty good for that reason. But it also does iodination reactions, which is undesirable. Now, that being said, iodine is a solid, so you can weigh it out relatively easily. It isn't a liquid, it's less toxic than bromine if handled properly, so I would say iodine's a little bit cooler than bromine, but because it's a worse oxidizer, that cancels out a little bit. So we'll put iodine in B tier. Let me know if you disagree with that down below. Now, fluorine, so few people can work with pure elemental fluorine. There's more people who can work with it in like a dilute solution in air, like, as a mixture of gases, like 3%, maybe 10% if you're really got a capable lab, but few people can work with pure fluorine, and that's because it's the most potent oxidizer, one of the most potent oxidizers anyway. Fluorine is no joke. Now, it's really hard to handle, so even though fluorine's really cool, I can't put it in S tier, so I think we're going to have to settle for A tier. Now, ceric ammonium nitrate, CAN. A really underutilized oxidant that's a very strong oxidant. So quite often we make cerium-based stains for TLC, and if you make like a couple of the different stains using cerium, you can stain like hydrocarbons. It's like a really potent oxidant. You see some CH oxidations with ceric ammonium nitrate in older literature, but it's one of the oxidants that hasn't seen as much use in modern chemistry. But it should make a revival because it's a really useful oxidant, and sometimes there's challenging oxidations. So I actually think ceric ammonium nitrate probably belongs in like B tier, maybe C tier. Because cerium starts with a C, we'll put it in C tier. Okay, chlorine trifluoride. This is an evil chemical. It destroys almost everything. It's, harder to deal with even than fluorine. It will like ignite sand and like actually burn sand. It will burn water. It's terrifying. Chlorine trifluoride is more terrifying than fluorine, but because it's not very practical for most syntheses, I'm going to put it in C tier. If you're an inorganic chemist and you use chlorine trifluoride, you can comment down below and let me know. I know a couple of you out there. You exist. So let's look at another one like Pcc, Pyridinium Chlorochromate. So Pcc is another good oxidant for making aldehydes. It's convenient in terms of being, a salt, so that's convenient, more convenient than chlorochromic acid. However, it still has chromium in it, so it's a little bit toxic. Now here we're not considering toxicity exactly, we're considering utility. And so because it's very useful for oxidation reactions, it'll usually stop at the aldehyde as long as it's dry. I think we're going to put it in A tier. Really good oxidant. Now MCPBA, it's pretty good too. It's a solid. You can stabilize it if you're worried about it detonating. but it can make epoxides. There's all sorts of oxidations you can do with MCPBA. It's a pretty cool reagent. I still haven't heard a good rationale for why we use MCPBA instead of perbenzoic acid. I think it must be just an artifact of how it's made. It might have been like a byproduct, so it was just more available and cheaper, and so we started developing chemistry around it. If you know anything about the history of MCPBA, please comment down below and I'll pin that comment, because I think that would be a really interesting thing to discuss in the comments. So MCPBA is pretty cool. It's a little bit annoying to remove, but you can quench it if you do a proper workup. So I think I'll put MCPBA in D tier, but you know, maybe it belongs in C tier. Now, oxygen gas, it's pretty hard to beat oxidant as an oxidant because it's in air. You can just use air for a lot of reactions. It's super convenient to handle. Now, if we're just talking about oxygen in its ground state, it's a decent oxidizer, but if we have singlet oxygen's terrifying. Singlet oxygen, if you were to breathe in a lung full of it, would just burn and just wreck your lungs. I'm not going to tell you how to make singlet oxygen, but that information is available online. And it's a crazy powerful oxidant when it's generated in its excited state. So oxygen, I think, is an easy S tier. Nitrous acid, another really great oxidant. A little bit hard to have on its own. Normally we just generate it in situ using sodium nitrite and some sort of acid. Another very oxidizing acid. Usually we'll oxidize nitrogen-containing compounds to diazo compounds or diazonium compounds using nitrous acid. Very, very reactive reagent. I think nitrous acid also belongs in S tier. Maybe I'll put it in A tier just because it's a little bit inconvenient to handle. Okay, potassium ferrocyanide. You may not have heard of this one before. So in a lot of research contexts, you can use this as like an electron transfer agent. So this can do one electron oxidations. Sometimes you can do further oxidations if you're using several equivalents of this. It's a little bit dependent on conditions. But you could, for instance, oxidize catechol to quinones, depending on the pH and the solvents that are used. But I've had a lot of success following literature procedures for converting catechols into quinones. I also have another video in the toxic series that I'm planning on doing involving potassium ferrocyanide. And if you want me to make a video on that, comment down below. So I'm going to put potassium ferrocyanide in a lower tier, maybe like C tier or D tier. Now, I'll probably put it in C tier, and let me tell you why. So it's really cheap, really easy to make, really cheap. It's a nice solid, you can just weigh it out. Usually it's a hydrate, but that doesn't matter for most purposes, especially if we're doing aqueous chemistry anyway. It's just a really good reagent if you can find an application that's relevant for it. Sometimes you can do deprotections of certain electron-rich benzyl-containing compounds with potassium ferrocyanide. That's just underutilized in chemistry. Super useful reagent. Potassium persulfate. So this can be a good radical initiator for polymerization. Can also be used in some transformations where you need to turn over a catalyst, get it back into a more oxidized state. You do see it used quite frequently, it or other compounds like Ozone as well in synthesis quite frequently. It's also a salt, so that makes it a little bit more convenient. It is a peroxide, so it's a little bit dangerous. I mean, all of these, most of these are dangerous, but it's a pretty useful reagent. I would probably say it's like, in terms of utility, like C tier, maybe D tier. If we compare it to things that we want to do more useful organic transformations with. It's a little bit dirty of an oxidant, but it's, you know, not too bad. So sodium peridate. Some of you complained previously when I talked about peridate with this structure because it's not an accurate representation of the actual form of peridate, and fair enough. There should be some hydroxy groups because usually it exists in some hydrated form. Now peridate or periodic acid are really useful for CC cleavage of 1,2-diols. It's also a salt. It's easily available. It's available to the amateur chemist. I think peridate's one of the most OP reagents in organic chemistry, and I think there's still not enough recognition of how useful it is. So I'm going to put sodium peridate in S tier. S for sodium. Okay, bleach, sodium hypochlorite. Everyone has a bottle of this in their house. Everyone's familiar with bleach. It's a strong oxidant. Our cells generate bleach to kill pathogens. There's certain... I don't remember the word for it, but there's certain small... things that your cells can make to trap invaders potentially and break them down using bleach. So we can generate that and use it, which is a little bit surprising. And it makes sense that, you know, we have an internal mechanism for this because it's a useful way to kill stuff and oxidize stuff. So very useful. It can be a little bit dangerous occasionally, but for the most part, it's pretty safe. So I'll put bleach in S tier. Okay, selenium dioxide. You may not have heard of selenium dioxide before, but selenium dioxide is really good for allylic CH oxidations. So the conversion of an allylic CH to an allylic alcohol is usually easy to do with selenium dioxide. There's also some other transformations you could do with selenium dioxide, for instance, to the alpha positions of carbonyls. So selenium dioxide, I've not personally worked with. It's a little bit toxic because it's a selenium derivative. Although it's not among the more toxic selenium salts, it's still a selenium salt. So it's convenient to handle in that sense, but it is very selective. So I'm going to put selenium dioxide in B tier. Okay, let's look at a couple more. So lead tetraacetate. It's a lead salt, so that's kind of fallen out of favor for us because we try to avoid heavy metals in most of our syntheses nowadays. But lead has been really useful for de-aromatization reactions, especially for like phenol-containing derivatives. So if you look on Reaction Flash, you'll find some really cool reactions that utilize lead tetraacetate, but because it's fallen out of favor, I think we have to put it in F tier. Now, select fluor. Select fluor is a very strong oxidant. It can be a 2-electron oxidant. It can also do other chemistry. It can be an electrophilic fluorine source. But it has been used specifically as an oxidant for certain metals or for certain catalytic processes. Now, I think as an oxidant, it's okay. Like, it's a strong oxidant. It's an NF plus reagent, but I would probably prefer its utility as a fluorinating agent over that of an oxygen. And because it has a fluorine in it, we'll put it in F tier. Ozone. Ozone is great. Ozone does some really cool chemistry. It kind of blows my mind that anyone ever even discovered ozonolysis, because even now with our modern techniques, it's kind of a pain to generate ozone unless you're chemical force and you're making and condensing liquid ozone. You know, most people don't have a way to get pure ozone and work with pure ozone. Normally you generate it from air. But because it's just using air, it's great. It's free. It's there, right? We have an ozone layer, but we wouldn't be able to utilize that ozone in a lab setting. Usually we have to generate it on our own. So ozone makes explosive stuff, which is pretty sketchy. It's also very harmful to living things because it can just wreck everything. It's a strong oxidant. It's so strong that I'm going to put it in S tier, but it's insane. Like, part of the smell that you get from any electronics is from ozone, because anytime there's like a little spark or something, you get the burnt metal kind of smell. It's a very, very specific smell. So ozone, it gets S tier. Now, divanadium pentoxide. This is used in the synthesis of sulfuric acid from sulfur dioxide. So first they convert sulfur dioxide into sulfur trioxide using a divanadium pentoxide catalyst. I don't personally know of too much use of this in traditional organic synthesis, but it's a really cool reagent, especially to see an early transition metal utilized as an oxidant. So it's kind of cool. I'm going to put it in E tier. Now, let's look at terbutyl hypochlorite. So I've made this before. It's stupid easy to make, just with terbutanol as well as bleach. Now, it's very, very oxidizing. I've had vials of this before that even if super duper parafilm taped shut, it will just chew away, and you'll see like a radius of effect around that vial where stuff is just getting bleached away from the chlorine that it generates. It's a really cool reagent to work with, and it's not water soluble, so you get a nice yellow oil when you make it. It's a really good Cl plus source, even better than bleach in most cases that I've used it in. However, it's terrifyingly strong. Pretty dangerous, but very easy to prepare. I'm going to put it in B tier. Now, osmium tetroxide, another really great reagent, but extremely toxic. And, you know, I could have put something like potassium osmate here, AD mixed beta, etc., and then it would have been a little bit better in terms of score. Now, it's so useful. It's just so useful that osmium tetroxide can dihydroxylate alkenes. It's a very useful methodology. It's just super toxic and super volatile as a solid. So I'm going to put osmium tetroxide in E tier for that reason, but it has so much potential. If we were able to come up with another alternative that was similar but less toxic, I think osmium tetroxide analogs would be great. Peridate's a little bit like osmium tetroxide in terms of you could do similar dihydroxylation chemistry, although it's not as generalizable as osmium tetroxide. So we've got several left here. Sodium perborate, it's another peroxide source, but in this case it's a boron derivative. This hasn't seen as much use in organic synthesis, but occasionally you do see it used. I think sodium perborate probably belongs in E tier. Now, sodium chlorite, this is used in the pinnic oxidation, the conversion of aldehydes to carboxylic acids. One of my favorite reactions, just because it's a really cool reaction. Really useful to convert aldehydes to carboxylic acids, one of the highest yielding methods that you see. However, you do have to prepare an aldehyde first. Now, it's a salt, you can handle it. The downsides are it generates chlorine dioxide, and sometimes you get chlorine radicals, hypochlorite as well. So you kind of have to quench the stuff you generate with it, but if you add in stuff to quench it, it's not too bad. So I think sodium chlorite probably belongs in A tier. You can comment down below to let me know what you think. Now, tempo. Tempo can be an oxidant. Usually we see it as a radical trap. There's a salt derivative of tempo called Fremmy's acid, which just barely didn't, or Fremmy's salt, which just barely didn't make the cutoff for this video. But tempo is still a potential oxidant. Pretty cool reagent. It's a stable radical, but it can be, reduced to an alkoxide. But it's pretty cool overall. Tempo, I think, belongs in D tier. Here we can see that we have a second osmium tetroxide. I don't know why that happened, and we will just delete it. Chromium trioxide. Chromium trioxide is essentially the precursor to Jones reagent, which I have over here, chromic acid. Chromium oxide, trioxide, the acid, and chromal chloride are all similarly good oxidants. I think all of them should be placed the same way where we placed PCC, except a little bit worse. So here you can see PCC is A tier. Now, because these are way sketchier to handle, chromic acid is doable. It's not too bad, but chromal chloride is terrifying to handle. Chromal chloride gets F tier. Chromium trioxide, probably slightly better. I guess we can go in E tier. And chromic acid can go in E tier as well. I also had potassium dichromate, but I believe I forgot to include that in here. So if I was to rank potassium dichromate, because it's a nice orange salt, it's a little bit easier to handle than the other forms of chromium, I think potassium dichromate goes in the C tier. Now, TCCA, this is your typical pool bleach. Sometimes you have the dichloro monosodium salt. This just generates bleach essentially in the pool and kills living stuff that you don't want to be living in your pool or at the swimming pool, such as stuff that other people have brought into the pool that should not be in the pool. So this keeps you safe in the pool. It's not very water soluble, so you can have a nice big white puck of it. It doesn't just immediately dissolve and react with all the water. Like if you used something like just pure bleach in the pool, it would be too high of a concentration of bleach, and then it would react with the light. So this just slowly generates chlorine. So it's a nice pragmatic solution. Dirt cheap, easy to regenerate, really good reagent. However, it'll also do chlorination chemistry. So because it does chlorination, we're going to put it in C tier. Now, Proxy Monosulfuric Acid. This is the acid derivative of Ozone. It's also known as Caro's acid. Pretty useful, a little bit scary. You can see we got a peroxide in there and a sulfuric acid. So this is a potent acid and an oxidizer. This is a little bit dangerous. So because it's a little bit dangerous, we're going to put it in B tier, but useful reagent. Now, manganese dioxide. You might not be familiar with manganese dioxide unless you've seen it in an alkaline battery. So alkaline batteries have manganese dioxide. However, you can also occasionally do allylic alcohol oxidations to alpha-beta unsaturated ketones or aldehydes, as well as propargylic, sometimes benzylic. So it's a useful oxidant. It's a very insoluble black powder, so it's easy to remove afterwards. Sometimes you have to do like a plug of silica or a distillation to get rid of every last bit of it. But it's a decent oxidant. Like I think manganese dioxide's underappreciated. I'm going to put it in A tier. Now, DDQ, you might not have heard of DDQ before. I don't have any other quinones in here. I was very tempted to put some orthoquinones and just like benzoquinone in here, but due to the massive number of compounds in here already, I had to cut off several of them. So DDQ is probably the most commonly employed quinone in organic synthesis. Benzoquinone on its own is also relatively common, and you could use this as an oxidizing agent for metals. You can do some deprotections of certain benzyl groups, like benzyl ether derivatives, for instance, or benzyl ester derivatives to like carbamates or whatever. So useful oxidant. Now the downside of this is it generates hydrogen cyanide depending on pH. And so because it generates cyanide, I'm going to put it in C tier, but it's a pretty useful reagent. Okay, terbutyl hydroperoxide and benzoyl peroxide. Both relatively dangerous. Now, terbutyl hydroperoxide can be useful for generating radicals, but in terms of its utility as a strict oxidant, I wouldn't say we see it used too frequently. Occasionally, you'll see it used for some transformations in organic chemistry, but I think terbutyl peroxide probably has to go in F tier because it's got a pretty low oxygen to carbon ratio. A little bit sketchy. Benzoyl peroxide slightly better. A number of you commented in a previous video that it's in acne cream, and yes, it is. It's used to prevent acne. But that being said, there are still several instances where people have had negative consequences as a result of explosions coming from benzoyl peroxide. So it's better in terms of stability than terbutyl peroxide. It's got more carbon relative to the peroxide. It's got a little bit of danger to it, but it isn't too bad. So we'll put it in D tier. Now, DMDO is a great oxidant, one of the best oxidants. Like, it's so clean. Acetone is your only byproduct. However, it's really dangerous. This can be extremely explosive. It's an analog of another acetone peroxide, which is frequently used in suicide bombings, which is terrifying. And if someone's not careful when they make this, they might make dimer or trimer, which can be really dangerous. So DMDO is really dangerous, but it's really cool. I think it probably is one of the best oxidants here in terms of being usually clean. Sometimes you see CH oxidations with it, though. But it's got a lot of utility as an oxidant. So we're going to put it in D tier, but it's a pretty awesome reagent. Hydrogen peroxide. Super useful, especially in its dilute form. It's pretty safe to handle. You can oxidize kind of everything with hydrogen peroxide, just sometimes you need to add in, like catalysts and whatnot. Sometimes you need to deprotonate it if it's an organic oxidation. But it's a useful material. If we were to combine this with sulfuric acid, which we have down here, we would have Piranha solution, and the combination of hydrogen peroxide with sulfuric acid makes you able to dissolve almost any organic material, more or less, especially if you use hot Piranha. So very, very dangerous combination together, but very useful. I think hydrogen peroxide probably belongs in S tier. Sulfuric acid, it's harder to use sulfuric acid as an oxidant in most cases, but because it's such a strong acid, it can do work. So if you like mix sulfuric acid with some metals, it'll oxidize the metal and you'll get hydrogen gas as a byproduct, like for sure. It's just, compared to some of these other oxidants, it's pretty lame. So for that reason, I think we're going to put sulfuric acid in D tier. Now, last but not least, we have potassium permanganate, used as a TLC stain. So if we want to visualize organic compounds that can be oxidized, potassium permanganate is an oxidant of choice for that. When we convert potassium permanganate to manganese dioxide, we usually see a change in color by TLC, so that's pretty useful. It can be used in organic transformations, however, it's usually too harsh to do most chemistry. It will usually chew molecules apart, however, there are instances where you can use it. So quite a while ago, Nile Red did a video making butyric acid from 1-butanol using potassium permanganate, following a prep from Vogel 3rd edition. And we're taught about it in undergrad. However, it's usually too harsh to be used in an academic setting as a reagent, other than for the staining of TLC plates. But because it's so useful for visualizing TLC, I'm going to put it in A tier. So hopefully you've enjoyed this video ranking the different oxidizers. It would really help out this channel if you left a like and commented down below, subscribe to the channel. And if you want to support us the most, you could support us on Patreon. But if you're an undergrad or high school student or someone who's not a professional, I absolutely don't think you should do that. So I hope you have a great day.